Hi, welcome to Finance 367's lecture video on the introduction to portfolio theory and covering some of the highlights of the Harvard Management Case Study number 1. In this lecture, I'll be um, building on what we talked about in class of trying to construct an optimal portfolio given two risky assets, as well as once you have a portfolio of risky assets, what proportion of it do you want relative to a risk-free rate? So we'll be diving into some of the numbers and tying that into what you guys would have answered in the case study. So let's go ahead and get started. As you recall in class, the portfolio problem is really separated into two, right? The first question you want to ask is, how much do you want to invest in the risk-free asset relative to a mixture of risky assets, right? So assume that there's a mixture of risky assets, let's say 15% Apple stock, 20% Tesla, 30% Amazon, et cetera, all the way up to 100. That's your allocation to risky assets. And then you want to ask yourself, how much of it do I want relative to a risk-free rate, like a treasury bill? And that's something we talked about in class. The second question we also want to talk about now is which risky assets to invest in, right? Because as I said, the first question is what percent, right, of risk-free and risky, right? That's question number one. And we talked about that in class, right, through the Sharpe ratio and the capital allocation line. And the second question now really ties into this portion. What do we mean by the risky portfolio, right? Like in other words, what comprises the risky asset portfolio? And this is essentially what people often call the separation property, that when you're doing portfolio allocation, it can really be divided into these two questions. So we tackled the first one in class. The second one we'll tackle in this lecture video. So let's give you some intuition on what we're talking about in the case discussion study, right? So the case study focused really on Harvard, but it really underpins the importance of university endowment money. So what I've shown over here is the ranking of the top 15 universities as well as their endowment funds, right? This is going back to 2019. And you can see that the University of Texas system is actually at number 2, right? So it's a big player. It's the second largest, second to Harvard, and it has a large endowment portion of money that's used to fund university activities as well as the university research budget and et cetera. So it's a really important investment problem for every university to tackle in how to use these investment funds and to how to use these endowment funds and to invest them in a proper way so that to fund university functions. So the University of Texas and Texas A&M, they take their investment funds and it's actually managed by this company called UTIMCO, right? And they're thinking about a lot of different questions. They're thinking about the needs of the current beneficiaries, right? They're thinking about what kind of current income can their assets generate. They're thinking about income stability as well, right? We talked about in class that volatility is one measure of risk. And it kind of depends on, as we measured through variance, how bumpy is our investment experience, right? Are we getting something stable or is there going to be a lot of risk involved? And that's something that UTIMCO also has to focus on when deciding how to distribute or design their asset allocation, as well as maintaining purchasing power of income. And that's also related to inflation, right? Because we talked about in class, if your nominal return, right, is let's say 8%, but inflation is also 8% or even higher, well, that means that your real return is going to be zero, right? Because although your assets grew by 8%, the purchasing power was also eroded by 8%, so your real return was actually net zero. The other thing that UTIMCO also needs to focus on are the needs of future beneficiaries, right? If they're thinking about scholarships in the future, right? They want to invest today for future scholarships. That's something that they're also very keen on, as well as the needs of donors and underwriters, right? Because they're also looking for alumni donations and investing that in a proper way as well for future income. And over here, I've kind of shown you a little pie chart, right, of their composition of their portfolio. We can see that a huge proportion of it is tied to domestic public equities, right? You could think of these as companies that you see on the New York Stock Exchange, like Apple, Facebook, et cetera. And they also have a significant portion in international public equities. And what you'll notice in this chart is that it's not just one color, right? Because if it was just one color, that wouldn't be very diversified. So one of the key tenets that you can glean from this pie chart is the importance of diversification, right? That UTIMCO considers a mixture of risky assets, right? They consider this entire mixture of risky assets when designing their portfolio allocation. And we talked about the importance of that in class, right? When we're trying to design a portfolio with low variance. And how do we get a portfolio of low variance? Well, we talked about it in class, and we'll go to a little more detail in a little bit. It's all about this covariance term, right? And we'll see that this covariance term actually dominates any variance terms. And just to kind of remind ourselves what is covariance, well, covariance is essentially the co-movement, right? Co-movement between two assets. So if the covariance between A and B is positive, that means they move together, right? And if the covariance of A and B is negative, then they move in opposite directions. And we talked about in class why we want assets, or the importance of having assets that have negative covariance or negative correlation. And that goes back to the diversification argument that if one stock performs poorly, ideally you'd want another portion of your stock to perform well to kind of cancel out or mitigate that downside performance. Okay, so that's why covariance that is negative tends to lead to a lower variance portfolio. So UTIMCO obviously has their own decisions in making their asset allocation, and they decided that this allocation of their portfolio gives them the best performance or best Sharpe ratio relative to the risk that they're taking. Okay, so it's also worth kind of highlighting a little bit something of a unique structure in the state of Texas, in that the state of Texas Constitution, actually starting from the genesis of it, has land appropriated specifically to generate income for the University of Texas, right? So in this flowchart, they have essentially a lot of acres of land in this area of Texas, and I'll be showing you an article that talks about it. And this land generates both mineral income, right, which comes from mainly from oil and gas, bonuses and rentals, as well as surface income, such as income from grazing leases, assessments, wind power, etc. And they take this mineral income as well as surface income, and that's essentially invested through a university fund, through the permanent university fund, and it's distributed through the Texas A&M University as well as the UT Austin University, right? So the question becomes, how important are these land grants, right? Is this something significant, and how big of a player is this kind of university fund, permanent university fund, through this land grants relative to UT Austin's fund? Well, a Bloomberg article actually shows that this endowment fund that I just showed was actually valued at 31 billion. Okay, and it was this that made it a big driver in passing Yale as one of the largest endowment funds in the country in terms of a university. So the question is, how big is it? It's actually a massive portfolio position relative to their assets, right? And it's also significantly low risk, right? There isn't too much risk involved in this mineral as well as surface income, right? Because the land is always there and it's always going to be able to generate income. So this is actually somewhat of a low risk investment and a high return. Okay, and we talked about in class that if you have a low risk and a high return strategy, that's something that investors want to be a part of, right? Because if we plot over here the expected return and the sigma, the standard deviation, it kind of points towards the northwest direction, right? And I would encourage all of you to read this article to kind of get some more intuition of how powerful this investment option is for Texas, the University of Texas State System, as well as Texas A&M University. Okay, so these are all significant drivers in the portfolio position of UT Austin and what drives their huge endowment. So let's go over the case study, right? So in the case study, we're asked to think about two assets or two stocks and to kind of understand their portfolio positions, right? To understand their expected returns when we combine them into a portfolio, as well as their variance when we combine them into a portfolio. And we talked about in class that, there's this really nasty equation when we're combining portfolios for variance, right? We know that the expected return of a portfolio is pretty straightforward. In fact, it's just the weight in A, actually I'll call it 1, the weight in 1 times the expected return of stock 1 plus the weight in 2 times the expected return of stock 2 plus ... the weight of n stocks, right? Expected return of n stocks. So if we want the expected return of a portfolio, it's simply the weighted average of the individual expected returns, right? And we talked about how this is a relatively easy expression to deal with, right? It's just simply a weighted average. And unfortunately, we also talked about in class that, well, the two portfolio situation, the variance equation is not so nice. In fact, if you talk about two stocks, it's actually weight 1 squared times sigma squared 1 plus weight 2 squared sigma squared 2, right? Ideally, this would have ended here, but unfortunately, we also have this 2 times weight 1, weight 2, right, times the covariance between return 1 and return 2, right? So, and we also talked about how the correlation between stock 1 and 2 is simply the covariance of 1 and 2 divided by standard deviation of 1, standard deviation of 2. So we can simply kind of substitute out. This implies that the covariance is equal to the correlation times sigma 1, sigma 2. Okay, so we know that this equation is really nasty for the two stock case, and we want to kind of ask ourselves, why is that the case? Well, kind of recall that the definition of a covariance, right, between 1 and 2 is going to be equal to the expectation, right? What is the expectation of? It's going to be R1, right, the return of the stock 1, minus the mean of 1, times the return of 2 minus the mean of 2. Okay, and we think about a portfolio of, the variance of a portfolio is going to have a lot of covariance terms as well. So if we were to kind of draw a covariance variance table, right? So let's say we have weight 1 over here, and then we have R1 minus mu1 right there. And then we also have weight 1 times R1 minus mu1. Kind of draw like a little mini table over here. We kind of want to understand why this equation is so nasty. Well, essentially, I also have, let's say, weight 2, R2 minus mu2, right? And we also have weight 2, R2 minus mu2. Okay, so what we can do over here is we can do kind of like the cross products between the two. So what I would do is what I plotted over here on this, X table over here is the weight ones relative to the return minus the average, weight 2 times the return minus the average, and I've done the same thing over here. And we take the cross product, we can take W1 times W1, that's W1 squared, and we take R1, and we take the expectation of this with the expectation of this, well, that's nothing more than just the variance. Okay? And likewise, we can take the cross product over here. This W2 times W2 is W2 squared. W2 squared. And then the cross product between R2 minus mu2 and R2 times mu2 is simply sigma squared 2. Okay, so you can see that the diagonals are essentially the variance terms, and that's going to be given by this guy over here and this guy over here. Okay, and we're not done, right? We also have these cross product terms as well. So what we get is W1, W2, right? Times now essentially the covariance of R1, R2. Okay, and likewise over here, we'll have W2, W1 times the covariance of R1, R2. And notice it doesn't matter if I do W2, W1 or W1, W2, they're the same thing. So when I want the total variance of the portfolio, I'm going to be adding up all four of these terms. So I've shown you that I've added up these two terms over here. That's given by this guy, this guy. Well, if I add up these two, they're the same thing. So I can put a 2 in front and I'll get 2 times W1, W2 times the covariance of R1, R2. So what I've shown you in this table is kind of the motive or a little bit more of the mathematical background behind this expression, right? And as you can imagine, if we go through to, we can also go to Wn, Rn minus mu n, right? Why stop at 2 assets? We can also go to Wn times Rn minus mu n, where n is some arbitrary number of stocks in your portfolio. You can think of like 10, right? And that's going to lead to obviously the diagonal terms Wn squared, sigma squared n, but you're going to have a lot more of cross product covariance terms, right? So if you'll notice, there's actually, if we have an n by n, number of stocks, how many covariance terms are there? Well, there's actually going to be n number of them, right? There's actually going to be n variance terms, okay? And how many covariance terms are there? Well, we take the covariance terms is essentially everything else in this box, right? Minus these diagonals. Well, if we have a square of n by n, the total number of things in this box is essentially n squared, right? If we have an n by n, it's n squared. But we got to get rid of all the variance terms. And how many variance terms are there? There's n. So it's actually going to be n squared minus n covariance terms. And if you just kind of stare at this and you ask how much more are there? Are there n? Is n bigger or is n squared minus n bigger? Well, clearly n squared minus n is a lot bigger. And that kind of underpins or kind of shows you the importance of the covariance in a particular portfolio, right? Because I just showed you mathematically that when you're looking at the variance of a portfolio, the number of covariance terms dominates the number of variance terms. So that's why the covariance is much more important than the variance of a portfolio. Okay. So let me go through like an example of, a two stock case, right? This is kind of what you had done in your case study. So let's say I look at Apple, right, over the past 10 years, right? So over the past 10 years, right? And they had an average monthly return of, let's say, well, actually did it. It's 2.56%. Okay. And they also had a standard deviation of 8%. And let's say Tesla over that same period, right, had an average monthly return of 5.84% and a standard deviation of 18.19%. Okay, so clearly Tesla's way more volatile, right? It's more than double the standard deviation of Apple, and it has a higher expected return or a higher average return. Okay, and let's say that the correlation over this period was 0.34. Okay, so I told you the average return, I've told you the standard deviation of both assets, and I've also told you the correlation between the two. And now I'm more or less done when I want to construct a portfolio allocation, right? And the question was, in the first problem, you're asked to kind of compute these returns, and it's not hard, right? You first need a price series of Apple, right? So if you have Apple price series, right? If you had the price over here, well, to compute the return, you would simply just take the percentage difference, right? If this was the return, let's say, I don't know, if the price here was 100 and then 110, right? I'm just kind of making numbers up. The return would be the over this particular month, right? So let's say this is January and this is February. If you want the return over this particular month, you would take the percentage change and that would simply be 10%, right? And on Excel, you would just kind of link this formula down. You would just keep taking the percentage returns over consecutive periods. And you would do the same thing for Tesla as well. And if we want the covariance between these two terms, well, we talked about that the covariance, right? Or if you want the correlation is equal to the covariance between Apple and Tesla divided by sigma Apple, sigma Tesla, right? Standard deviation of Apple, standard deviation of Tesla. Well, this comes from the data. This comes from the data. You can compute this manually, or you can use an Excel function. This also comes from data. And by dividing the two, you automatically know the correlations. Okay? So now, if we want to construct a portfolio of these two assets, right? So we want a portfolio between Apple and Tesla, right? So if you want portfolios, we talked about in class, a portfolio is purely defined by weights, right? So these are purely defined by weights. If you tell me the weights on Apple, you tell me the weights on Tesla, I'm done, right? I just take the weighted average between the two. So let's say I want an equal weighted average. Well, an equal weighted average just says equal weights, right? So I can go 50-50, right? 50-50 on Apple, 50-50 on Tesla. And if I want the expected return, as we saw previously, the expected return is easy, right? You would just take 1/2 the mu of Apple plus 1/2 the mu of Tesla. And that would give you essentially the weighted average of the portfolio. And likewise, we can also throw like 3/4, 1/4, right? And that would give me, I would need to compute 3/4 of Apple. It's 1/4 of Tesla. Okay. And there's another aspect of it that's called market weighted average. Okay. And we're taking the market weighted average. We're no longer saying let's go equal weights, 50-50, etc. What we're saying is let the weight be the market capitalization of a particular company, right? So we know that the market cap is defined as the price times shares outstanding. Okay, so you can think of the market cap as essentially like the size of the stock in terms of the public markets, right? Because you're taking the number of shares that are out there and you're taking the price, which is dictated by the market, and you're multiplying the two to get like the total market value of the company, right? And we're taking the market cap weighted average. Well, we're asking ourselves is, first of all, we're having different weights, right? So the mu A and the mu T aren't changing. What we're changing is these weights, and the weights better add up to 100%. So what we're going to say is let's say the market weight now of, let's say, Apple. What we're going to do is we're going to take the market cap of Apple and we're going to divide it by the total market cap. And in this case, the total market cap is just the total market cap that's available to us, which is just Apple and Tesla. So what we would do is we would take the market cap of Apple divided by the market cap of Apple plus the market cap of Tesla. Okay, so that's going to be our denominator in total market cap. And obviously, if we have 3 assets, we would take the market cap of, number 1, divided by the total market cap of 1, market cap of 2, market cap of 3, because that's the total market cap in our universe, right? And that would be our market cap weighted average, our weights associated with Apple. And the market cap weight of Tesla, what you would simply just replace the numerator with the market capitalization of Tesla. And you can double check the math, but the weights, once you compute the weights, they're going to add up to 1 as well. Okay, so let's say I wanted to construct a portfolio now, right? And what I'm going to decide is I'm going to decide some sort of arbitrary weights, right? So this is kind of also what you did in the case study where I'm going to just kind of decide some arbitrary weights and look at their expected return. Okay, so let's say, all right, here's the expected return of the portfolio, and here's the standard deviation of the portfolio. Let's say I went 1-0. What is 1-0? 1-0 means I'm 100% in on Apple, and I don't want anything to do with Tesla, right? Well, if I'm 100% in Apple, then my portfolio is just simply Apple. So my portfolio's average return is going to be exactly Apple's. So 2.56 and 8%. Okay, so 2.56. Sorry, 2.56 and 8%. Okay, and likewise, let's say I went 100% Tesla and nothing of Apple. Well, my portfolio would look exactly like Tesla because I'm all in on Tesla. So my portfolio's average return would be 5.84 and 18.19 would be the standard deviation. Okay, so that would be 5.84, 5.84, and 18.19. Okay, so essentially what I've done is I've looked at the two extremes, right? If I go 100% Apple, 100% Tesla, that's also a portfolio because as I mentioned before, a portfolio is simply defined by weights. And I've told you the weights, in this case, 100% of one thing and 0% of another thing. That's entirely valid as well. Okay, but let's talk about something more interesting. Let's say I go 75% Apple, and what does this have to be? Well, it has to add up to 1, so that's have to be 25% of Tesla. Or you can take a weighted average, and I encourage you to kind of do the math yourself. The expected return is going to be 3.38. Okay, and that's a very simple calculation. You take 0.75 times this, 0.25 times this, and you can get 3.38. Standard deviation of portfolio is a lot trickier, right? We talked about this. It has those square terms and the covariance and the correlations, etc. And I encourage you to kind of go through the math, but you're going to find that's 8.67. Okay, and we can also go 50-50. Again, the expected return component is very easy. You just take the 50-50 average of the two. And the standard deviation is going to require some work, but not too bad. And it's going to be 11.10. Okay, and then we can also go 0.25 and then 0.75. And that would give you 5.02 and 14.44. Okay, let's just kind of take a look and just kind of get some intuition of looking at these numbers because a lot of numbers on the board, these were just computed just from pure math. But let's just see what intuition we have. Okay, when we're going down this column, what we're saying is we're going to get rid of some Apple and we're going to load up on some Tesla, right? Because that's what it's showing. Your weights in Apple are going down, your weights in Tesla are going up. What's actually happening to our portfolio? Well, the expected return is actually going up. And let's ask ourselves, does that make sense? We're loading more into Tesla and less into Apple. And as a result, the expected return of our portfolio is growing. Does that make sense? Well, it's got to make sense, right? Because Tesla has a higher average return. And if you're loading into something that has a higher average return, it would make sense that your portfolio would also sort of behave like that asset that you're going into, right? We're going towards an asset that has historically done better than the other asset. So as we get more of that asset, of course, our expected return should also increase. Let's also look at our risk, right? As we're loading into more Tesla, what's happening to the portfolio standard deviation? Well, it's actually also increasing, right? Why is it increasing? Likewise, the standard deviation of Tesla is way bigger than the standard deviation of Apple. So it would make sense that as you're going into a more volatile security, the portfolio of that, the volatility of that portfolio should also be much more volatile, right? So it makes sense from this intuition. So now what we're going to do is we're kind of going to draw a plot over here, right, of, standard deviation of the portfolio. Sorry for these non-straight lines. Okay, expected return of our portfolio. Okay, and let's say, I don't know, let's just put 5 over here, 10, 15, 20, right? And let's just go 2, 4, 6, 8, 10. Okay, so that haven't done anything yet. All I've done was just plot a y-axis, x-axis, where the standard deviation of the portfolio is on the x-axis and the expected return of the portfolio is on the y-axis. So what I'm going to do now is I'm going to take these numbers from this table and I'm going to plot it onto this figure, right? And let's go through the first extreme. Let's say I'm all in on Apple, right? So in other words, this first row over here. The expected return I'm going to get is 2.56, and the standard deviation I'm going to get is 8. Okay, so remember that 2.56 and 8. Well, 8 is going to be somewhere around here, and 2.56 is going to be somewhere around there. So let's just call it right there. Okay, so this portfolio corresponds to all in on Apple. Okay, so you don't see any weights on this figure, but they're kind of behind the scenes, right? I've said that let's imagine you're all in on Apple. This is your expected return. This is your risk. Let's say we're all in on Tesla. Okay, so the standard deviation is 18.19, 5.84. So 18.19 is about here. 5.8, kind of just eyeballing it, is somewhere around like here. Okay, so that's all in on Tesla, right? And if you're all in on Tesla, your performance is going to look exactly like Tesla's, okay? And, we can kind of, pick another point here. I don't know, let's say 50-50, right? So 50-50, you're at 4.2 and 11.0. Sorry. So 11.0 is about somewhere there. And you're looking for 4 point something. So, oh, you're kind of around here, right? Kind of. And you can kind of keep plotting these out, right? I'll leave that as an exercise. And what you're going to notice is you're not going to get something linear, right? You're not going to get a straight line between Apple and Tesla, but instead you're going to get some sort of a bullet-shaped curve that actually passes through. This is not as nice as I would have hoped, but you're going to get some sort of bullet-shaped curve that looks like this. And it's really interesting because why are we getting a bullet-shaped curve, right? We've been dealing with some, linearities, but the key component is the nonlinearity associated with the variance term, right? As we saw before, the variance term has a lot of nasty expressions with squares and some covariance and correlations, and that's what's driving this bullet-shaped curve to, arc in this particular way. Okay, and we're going to call this the efficient frontier. Right? Well, we're actually going to call the upper component the efficient frontier. Can't spell frontier. So the efficient frontier is the set of possibilities that an investor can be a part of, right? As we mentioned before, all these points correspond to different weights in this table, right? If you wanted all Tesla, you'd be here. If you wanted all Apple, you'd be here. If you wanted some 50-50 mix, you'd be somewhere in the middle. And we can vary these weights to sketch out and draw out this efficient frontier. Okay. And the reason it's called efficient, well, technically the upper portion is efficient, is if we were, I don't know, let's say at a point here, does it make sense to ever be at a point here? Right? Does it ever make sense to find weights so that you're down here? Well, let's just kind of think about what this really means, right? We're saying we're at a standard deviation of, let's say, I don't know, this might be 11. This black line, again, is all the available options to us. Do we want an expected return down here? Or do we want an expected return all the way up here? Because they're both available to us because they're in the black line and they both have the same level of risk, right? Well, any person would obviously say, I want to be up here because it has a higher expected return with the same level of risk. So the efficient frontier, we're often going to refer to as this upper portion of this bullet-shaped curve, okay? Now, we can also ask ourselves, what drives this bullet-shaped curve, right? What happens when we talked about in this initial problem what the covariance was, right? I think I said before that the correlation between these two were 0.34, right? That's not a super high correlation. It's also not a very low one. But let's say we had a correlation of, I don't know, let's say negative 0.5. All right. So that means they move in opposite directions to each other. What's going to happen? Well, what ends up happening is this bullet-shaped curve is actually going to shift outwards towards this direction over here. Okay. And what this is saying is you're going to get essentially less portfolio risk, right? Because we're moving to the left, we're getting less portfolio risk, which is on the x-axis. And again, this is what is driving this. It's this correlation between the two assets. So this correlation is going to dictate how much we pull over towards the left. And that's something that we like, right? Because we're pulling towards the left, we're having lower and lower portfolio risk, right? And we can even go to the negative extreme. So we know that correlation is actually bounded by -1 and 1. And if we were to go to the extreme, what ends up happening is you would actually get a bullet-shaped curve, no longer bullet-shaped, but kind of like an edge, right? Kind of like a little sword action here. There's a little triangle. And notice that you're able to achieve this point over here. Okay, so with a correlation of -1, you're no longer in a bullet-shaped curve world, but you're instead in a triangle world, right? Which I've drawn over here. And notice that what this point is. This point is a zero variance portfolio. Okay, and that's pretty remarkable because what we're saying is if we have a portfolio in which the two assets are perfectly negatively correlated, which means one goes up 5%, the other one goes down 5%, you can construct a portfolio in which the variance of that portfolio is zero, right? And essentially, if you have a portfolio with zero variance, then you're risk-free. So we'll notice that this point is actually also can be the risk-free rate, right? And the intuition behind this is if you have two assets that are perfectly negatively correlated, well, you can kind of just mitigate when one goes up, when one goes down, one goes up by the same exact amount so as to cancel out and you can get a zero variance portfolio. Okay, so it turns out, right, and I can kind of just write this out mathematically. You don't necessarily have to worry about this. This will be in your textbooks, right? So if we were to kind of, generalize this, right, the variance of your portfolio is going to be 1 over n times the average variance plus n minus 1 over n times the average covariance. Right. And as you can see, right, as n goes to infinity, right, this kind of goes into like the little calculus limits. This term over here, since this is the denominator, is kind of disappear, right? It's going to go to kind of 0. But this term is not, right? If you remember like your early calculus classes, the limit of n minus 1 over n as n goes to infinity is going to be 1. So this term is going to be more or less 1, and you're going to be left with the average covariance. And this kind of goes back to what I said earlier in that the variance of your portfolio is going to be dominated by the covariance because there's a lot more covariance terms if you'll recall, right? There, in fact, just to kind of write it out again, there's n squared minus n covariance terms, and there's only n variance terms. So the covariance is going to dominate the variance, and as a result, the variance of your portfolio is going to be heavily driven by the average covariance. Okay, and so we can kind of, just plot this out over here, right? Let's say this is n, which is the number of stocks in your portfolio. Okay, and this is the portfolio standard deviation, right? So kind of what I'm plotting here. And you'll notice that if n, as it goes bigger, you're going to kind of asymptote down towards essentially the average covariance, right? And it's never going to be zero, right? It's never going to be zero because you're always going to have this covariance risk, right? And investors, when you're investing in a portfolio, you're being compensated for this covariance risk. And we'll talk a little bit more of this in class. But this is kind of the intuition behind this, right? Because no matter how well diversified you are, right? If you have like 1,000,000 stocks, 1,000 stocks, what have you, what this equation is saying is that the variance of your portfolio is going to asymptotically approach the average covariance, right? And if the average covariance is zero, then it would be zero. But you're going to asymptote over down to the average covariance. Okay. So I want to talk about another portion of the case study, which had a little bit of calculus involved, and I kind of want to go through some of it in case some of you are having a hard time with it. But essentially, whenever we're dealing with some minimization or maximization, right, you always want to think of calculus. Why? Because when we're doing calculus and we're optimizing something, we're essentially going to be taking the derivative, and setting it equal to zero and solving. Okay, so that's the kind of the name of the game whenever you want to optimize something. And if we were really to dive deep into the intuition, which we won't, I'll just kind of give you a brief preview. What is a derivative? A derivative is a rate of change, right? So if we think of something like looking like a parabola, it's essentially going to be the slope of the tangency points, right? It could be slope here, we just slope here, and the derivative is going to change at every single point. And when we're taking a derivative, what we're asking ourselves is, find me the point in which the average change here is zero, right? The slope here is zero. So that's essentially what we're doing, right? We're taking the derivative, which is all these slopes of these lines, and we're pinning down the point in which the slope is unchanging, equal to zero. And that's going to be dictated by this optimal, right? Which we'll call x star. Okay, so that's kind of the intuition of why we're taking the derivative. So if we have the variance of a portfolio given by, let's say, A, right? The weight of A, we're assuming two stocks, right? Squared plus, and now if it's two stocks and we have the weight of A being weight of A, then the weight of B has got to be 1 minus the weight of A, right? Because they've got to all add up to 1. So we can square B plus 2 times the weight of A. And again, the weight of B is 1 minus the weight of A, right? Times the correlation between A and B times the sigma A, sigma B. Okay, so I haven't really done anything. I've just kind of written out this nasty equation with substitution of weight of B as 1 minus weight of A. Okay, so I can rewrite this term here. I can rewrite this term as 2WA, right? Correlation, sigma A, sigma B, right? Minus 2 weight A squared, correlation, sigma A, sigma B, right? So I've just kind of just rewritten this, right? I can certainly do that. Okay, so now what I want to do is I want to essentially expand. I want to essentially take the derivative of this expression, right? So now I'm going to take derivative. And if you'll recall from your derivative rules, if with respect to WA, okay, why with respect to WA? Because I want to find the optimal WA such that the derivative is equal to zero, so that we're unchanging, right? So if I take the derivative, you'll remember from your first year calculus, you take this exponent, you bring it down, you subtract 1, so you get 2 WA, right? Sigma squared A, right? Minus, so I'm going to bring this 2 down, so 2, right? 1 minus WA sigma squared B. Now, why is there a minus sign here? There was a plus. Well, you're also going to have to recall the chain rule, which says that if we take the derivative of the expression, we got to remember to take the derivative of the inside, which in this case is -1 with respect to A. Okay, plus with respect to A now is 2, right? WA here is just simply going to be the things that are multiplied by it. Is it rho correlation sigma A sigma B, right? Minus, bring this guy down, that's 4 WA correlation sigma A sigma B. Okay, so all I've done is just taking the derivative, right? And what I want to do now is set this equal to 0. Okay, so I see a lot of this is a pretty nasty expression. Hopefully this gets a little better, right? What I'm going to do is I'm going to divide everything by 2. could certainly do that, right? That'll cancel this out, that'll cancel this out, that'll cancel this out. That won't cancel this out, but it'll bring a 2 over to here. Okay, so now what I want to do is I want to bring WA all on one side, right? So WA, right? What's left over here? Sigma squared A, right? What else do I have over here? I have plus WA sigma squared B, so plus sigma squared B, right? I have, so what else do I have? I also have this term over here, so minus 2, right? Correlation, sigma A, sigma B. Okay, so I've taken care of this term, I've taken care of this term, I've taken care of this term here. Okay, and that's going to be equal to, I got to bring this over here, right? I'm going to bring this to the other side. I'm going to get sigma squared B, right? Minus, right? We also have this term over here, which I've forgotten about, right? Minus sigma A, sigma B times rho. Okay, I'm almost done. So now I can just kind of solve this. WA is sigma squared B minus A, B, rho, right? Just divided by this expression, sigma squared A plus sigma squared B minus 2 rho sigma A, sigma B. Okay, so this now is my optimal level of weights so as to minimize, again, the portfolio's variance. Okay, and of course, you know sigma squared B, you compute that, you know all these terms, and that would give you the optimal weights in stock A. Okay, so you plug all these numbers in and you would get the solution. So now let's shift gears a little bit, right? And let's kind of look at some figures, right? And, we kind of talked about this, can think of this as WA, and this is WB is just simply 1 minus this, right? And you also have the risk-free rate. And you'll notice over here, this is the point of the equity, right? So this is the expected return as well as the standard deviation of the equity point. And this is the standard deviation as well as the return of the domestic bonds. And similarly, once you're given the correlation, you can sketch out this parabola or this bullet-shaped curve as I had done before with Apple and Tesla. And I can draw over here the risk-free rate. Okay, so that's everything that we've talked about, right? We've talked about this is the easy one, and we've kind of just did the math and calculus of this. Okay, so we want to ask ourselves now is, with this expression, right, if we plug everything in, what weight of equities do we have such as to minimize the variance, right? And the minimum variance portfolio is going to be given by the point in which you can't go any more left, right? Because left means, well, left to right is variance, and the more left it is, the less variance. You can't go any more left in this, right? And if you were to plug all these in, you would get the weights would equal to 11.2%. Okay, and if you know the weights of this, you would simply just do 1 minus this to get the weights in bonds. Okay. Okay, so now we want to ask ourselves, so we know this point over here, right? It's an interesting point. It's the point of lowest variance. So now this goes back into the first question, right? So remember, the two questions are how much of a portfolio do we want, right? Like what weights of equity, what weights of bonds, we've pinned that down. So the question now becomes, if we were to introduce a risk-free rate, right? And a risk-free rate is going to be given by this point over here. What are the proportions of that risk-free rate do I want? And what proportion of weights do I want in this risky portfolio that I've just constructed between bonds and equities, right? And the answers are going to really depend on what the risk-free rate is, right? And what I can do is, let's say I wanted to consider a portfolio between equities and the risk-free rate. Well, I would take the equities, I would take the risk-free rate, I'm going to draw a line between them. That's going to be given by this blue line. Let's say I want to consider a combination between bonds and a risk-free rate. I would take the risk-free rate and I would take bonds and I would draw a line between the two. Okay, that's as simple as that, right? You pick, what you want. You want only equities. You want the risk-free rate. You draw a line between the two. You want only bonds, risk-free rate. You draw a line between the two, right? And you can also have a mixture between the two, right? Let's say you can be a point out here. You can also draw a line over there. The question now becomes, what is the optimal line to draw? Right? Because, is it the orange line better or is the blue line better? Right? That's a valid question, right? What is a better line? And it turns out that, again, as we said before, everything on this bullet-shaped curve is afforded to us, right? So why would we stop over here when we can go over out here to this blue line, right? And the question becomes, what makes the blue line better than the orange line? Well, it turns out that the slope has a really interesting, interpretation, right? We talked about this in class, that it kind of just jumps out at you, right? So what is the slope equal to? Rise over run. Well, the rise is going to be the expected return of the portfolio, right, minus the risk-free rate, right? That's given by this vertical distance. And the x-axis is just simply going to be given by the standard deviation of the portfolio, which is over here. Now, you stare at this, and you stare at this, and you stare at this, and hopefully something jumps out at you as being the Sharpe ratio, right? We talked about this in class. Remember when I kept telling you to stare at that equation, and the Sharpe ratio just jumped out at you at the slope of the capital allocation line? The same thing going on over here. And we talked about in class, do we like a high Sharpe ratio, or do we like a low Sharpe ratio? Well, we got to ask ourselves, what is a Sharpe ratio, right? Sharpe ratio is going to be the ratio between the risk premium relative to the risk per unit risk that you're taking on. And clearly, we'd like more of a Sharpe ratio. So in other words, we'd like a higher and higher slope. So it turns out that we can do a lot better by this orange line, right? This is what we're called the tangency portfolio. Tangency because it's tangent to this bullet-shaped curve. And this is going to be given by the maximum, oh, it's actually written right here. I'll just write it again. Maximum Sharpe ratio, right? You can't do any better than this. Can you go out here? Can you go out there? No, you can't, because it's not touching the bullet-shaped curve. The bullet-shaped curve is all these opportunities that are available to this investor given equities and bonds. So you can't even go out there, right? You can be in this orange line, you can be this blue line, and you can barely be on this orange line. But barely is good enough for us because that's going to be given by the highest risk premium relative to per unit risk that we're taking on. Okay, and the capital allocation line dominates all other portfolios. Okay, and so again, this separation property that we're talking about before is we're going to assume that all investors are going to choose the same portfolio of equity and bonds, right? So now that we've pinned down this tangency portfolio, we've said that this is the best portfolio that one can have, right? This is the best portfolio one can have. So we all want to be on this tangency line. Now, what differs is how much of this portfolio do we want? Right? Do we want all in on this portfolio and none of this risk-free rate? Or do we want, I don't know, some 50-50 of it, or do you want some 75-25, or do we want none of it and just go all into the risk-free rate, right? Maybe we don't want any of that smoke, right? We want to be all the way out here. That's going to depend on your risk aversion. All right, we talked about it in class. What is risk aversion? It's how scared you are, right? So if you're super scared, we all agree in this room that this is the best portfolio, but I don't want that smoke. I want to be down here, right? But let's say you're not very risk averse, then you'll be all the way out here. Maybe you might even be out here, right? We talked about what that means, right? You're having a weight greater than 100%, which means that you're shorting the other end. Okay, so and why stop here, right? We can talk about different kinds of assets, and if you have two different types of assets, the correlations, you draw a bullet-shaped curve. You give me another two different assets, their correlations, you draw another bullet-shaped curve, and you keep going on, and you can kind of trace all of these out. Okay, and you can form, essentially, you can even form portfolios of portfolios. Okay, so then it really kind of becomes, what is the minimum variance frontier, right? And we've kind of talked a little bit about this before, of the intuition of why we want to be on the upper shape curve, right? So this kind of looks like a nasty math equation, but what you want to ask yourself is, it's not too hard, right? So we have expected return over here, standard deviation of the portfolio here. Forget this math for now. Just don't even look at this math. Look at this parabola. What I'm saying here is fix me an expected return, okay? Fix me an expected return. I don't know, let's say of this level over. Let's see how I want to think about this. For every level of expected return, right, I want to be in a place in which I have the lowest variance. Okay, I don't want to be out here because I can do much better by having a lower variance, right? I can be much better by going down here. Okay, so fix me another expected return level. And let's say I'm out here. Find me a point to bring me back to a lower variance here. And that's what this equation is looking at. Okay, so let's look at this. I'm going to force my return to be at some bar, right? Let's say this is that bar here, right? So fix an expected return level. So that's on the y-axis. Find me the point. And if you find me the point, that means give me the weights. Choose me the weights such that I can minimize my variance. In other words, give me some weights to bring my variance to as low as it can be. Okay, so in other words, fix me a weight, fix me an expected return, RP bar, choose weights for me to bring me to my lowest variance. Right? That's all this is essentially saying. And this looks really hard, but you can actually use some optimization softwares to, and you've done that in Excel in your case study, to choose your weights using solver such that to minimize the variance given a level of expected return. Okay. Okay, so to just kind of wrap up, right? So when we're taking what we're doing in this problem is mean variance optimization, right? What we're saying is, we have a stock, we have a bond, we know the correlation, so we can automatically trace their bullet-shaped curve. Then we introduce ourselves to the risk-free rate, and we draw a line, and we try to find a tangency point. And the tangency point is really going to dictate essentially, the maximum Sharpe ratio, right? We talked about what we mean by maximum Sharpe ratio, and it's essentially going to be the point in which we can do no better. Okay. And the last question in this case study kind of asks is, are these assumptions sensible, right? Do we actually believe this analysis? And it really comes down to whether you believe that the historical average is indicative of the future, right? Because as investors, we're thinking about what do we want to buy today because we want to have a higher return tomorrow. The past is the past. But what we're doing is we need a measure of the expected return. So we're proxying that using the historical average. But more importantly, we're also looking at a snapshot in time, right? So in other words, when we're studying, we looked at the 10-year period here. And we studied their expected return. We studied the standard deviation. We also studied the covariance, right? Or the correlation between the two, right? Correlation. And the question becomes, is the correlation or all these parameters stable, right? Because we need all these parameters in order to draw the bullet-shaped curve. But what if the correlation were to change into the future, right? I mean, this is kind of an open-ended question. If you believe that everything stays the same, the correlation we saw over the past 10 years is indicative, then you're good, right? You're good. You can draw your bullet-shaped curve, etc. But what if, the past 10 years had a correlation of, I don't know, 0.2, but in the future, you had a correlation of negative 0.6. What does that mean? Well, we saw how important the correlation was, right? It's really going to dictate the shape of your bullet-shaped curve, of the bullet-shaped curve. So if your correlation in the future, isn't indicative of what you see, moving forward, that's really something important to think about and in constructing your mean variance optimization. Okay, so I hope this is a nice overview of the case study and diving a little bit deeper into portfolio theory. And in class, we'll be going through, building off of this and going on from there. Okay, so thank you very much for watching.